Let's do a few more, and this next one, actually the next three, have very practical applications. So up until this point, it's been like random equations that we rotate, and it's like, okay, yeah, whatever. But now, this is very practical, and this is the kind of thing that is manufactured. I don't know if it's actually manufactured with this type of equation at Timken, but we'll go with it. Timken Corporation, they have a manufacturing plant in Randleman. They make bearings like the one shown below toward the plant. Really neat place. And so if I wanted to know the volume of this that I'm coloring right here, then basically it would be this shape but rotated. And so I've given you some equations that we're going to rotate, but we have to figure out what's on top, what's on bottom, what functions are on the top, what functions are on the bottom, what the integral is going to look like. So we know there's an integral, so let's go ahead and put it. We know there's a pi because we're rotating it, right? Because if you keep reading the problem, we're going to find the volume of something that's being rotated. So here goes. We know x-axis is going from 2 to 4, so that's no secret there, and that's the easy part. But now we have to figure out what's on the top and what's on the bottom. So here are our equations. X equals 2 and x equals 4. Well, we knew that. We've already got that into consideration. That actually told us what the limits were that go there on the interval. And then we have y equals 1/4 x plus 2.5. That would be this. And then y equals 4. So actually figuring out which one's on the top is not hard, and figuring out which one's on the bottom is not going to be hard. So 4 squared minus, and then 1/4 x plus 2.5, and all that is squared. And let's put the dx, and let's keep it real, because we're going to have a problem here. Notationally, this is very wrong until we put all this together. So let's just kind of, we could type it at this point and we could figure it out, and that'd be pretty easy. However, I just want to reinforce some ideas here. If we rotated that around the x-axis, we would get a volume. If we rotate that around the x-axis, we would get a different volume. Rotating the 4 gives us all the volume of all that stuff rotated, and it's going to make a cylinder. Rotating this will give us the volume of that rotated around, and it's going to be like a truncated cone. But we subtract this area, this volume, I'm sorry. So that's why we're subtracting that. Just wanted to throw that out there. And now we get to the easy part where we simply type it in. By the way, there are different names for this. There's a washer method and a disc method and a shell method, and they're fantastic, and they have fantastic names. But I'm just going to be real honest with you. I have found it best just to say this is pi r squared, and we'll have to subtract away what we're not using. And I just found that to be the best way to explain it. Hope I'm not oversimplifying it in doing that. There we go. I'm making sure I typed it right, and I did. Left the pi out, but that's okay. And so what we have here is 65/6 pi, or if you want to get all crazy with it and turn it into an irrational number, you could. 34.034 cubic units. Let's see. How's it measured? Doesn't say. They do come in a variety of sizes, like really big ones for aircraft and or space shuttles. They actually manufacture things for that. And tiny, tiny, tiny little ones that would like barely fit. You could barely see them on the end of your finger. It's amazing. Really cool. All right, a donut. You know what a donut looks like, and technically it's known as a torus. That is the mathematical name for it. Is created mathematically by rotating a circle about the x-axis. Find the volume of the torus created by rotating this circle, this one right here, pictured below about the x-axis. All right, well, I have no idea what I'm doing. I do, but I'm not telling. So if you don't know either, start with what you do know. You know that much. We're rotating something, so it's pi times something squared. We're rotating it about the x-axis, so this is going to be dx, not dy. And then we need to figure out what goes here. We left plenty of space. Now, interval goes from 2 to 4, so that's no secret there. And then we have to figure out what the equation is. Well, the equation of this thing is, let's find out. So what we're going to have is a center at 3, 2. I'm about to write the equation of a circle, by the way. A center at 3, 2. So x minus 3 squared and y minus 2 squared, and that equals the radius squared, which is 1. And we're going to solve it for y. All right, so let's do that. So 1 minus, don't FOIL that. Don't FOIL that either. You're wasting your time. So 1 minus x minus 3 squared. And that would equal all this stuff. And we'd have to square root it. And then we'd have to add 2 to it. So that's it right there. Now, that's it, but that's wrong-ish. Okay, this would only give us the top part of the circle. Well, that's okay, because we still have to do like top minus bottom. So we're going to have 2 plus, I'm going to have to move that dx over. I'm not going to have nearly enough room. Sorry about that. Thankful for whiteout. So 2 plus square root of 1 minus x minus 3 squared. And all that gets squared. And then we will subtract away the bottom part. And the bottom part is the square root of this stuff, but we don't do the plus, we do the minus. So then we'll do this, 2 minus the square root of 1 minus x minus 3 squared, all squared dx. I have left off some brackets or parentheses. And in a situation like this, there is so much room for error in typing this in that I find it easier to type them in as y1 and y2 and go from there. And we could have been doing that all along, but it's probably not the most efficient way until you get to a crazy one like this. So I'm going to start typing that. So we're going to have 2 plus the square root of 1 minus x minus 3 squared. I'm going to just glance at it and make sure it's exactly the way I want it to be. It is. And then 2 minus square root of 1 minus. Now, why am I doing this here and not under the integral or in the integral? Because when I put this in the integral, I'm going to have parentheses around it and square it, and it's going to be a mess, and I'm going to have all kinds of stuff, and I think it's just cleaner if you do it this way. Personal preference. All right. By the way, if you were to graph this, and I'm going to just really quickly, you'd have a circle. This one's going to look like an ellipse, and it doesn't look like it meets, but it does. It actually does. Just, you know, resolution issues on the calculator and the way they compute things, but that is a circle. There's the top, there's the bottom, 2 different colors. So let's do it. Math 9. We're going from 2 to 4. There's a pi in the front, and it is going to be y1 squared minus y2 squared with respect to y, with respect to x, not y. This one's probably going to be very irrational. Undoubtedly will be. This is going to take it a minute. Or a day and a half, we'll see. It's that, and by the way, if you were to press math and press enter on fraction, you're not going to get anything. It won't turn it into a fraction. See, it tells you. So let's just go ahead and multiply it by pi. And this is going to be 39.478 cubic units, whatever those units are. And that actually is how you would figure out the volume of a donut. If you ever wanted to know, like how much donut you're eating. Probably measure that by calories instead of volume, though. Okay, a tank on the wing, not the sing. I'll correct that before I print that off for your copy. But a tank on the sing of a jet aircraft is formed by revolving the region bounded by that graph around the x-axis and the x-axis about the x-axis, where x and y are measured in meters. Okay, up until this point, we've not had any units. We've just been like, okay, yeah, it's cubic units, whatever. We didn't even write that because they didn't tell us, but now it better be cubic meters when we're done. So let's put the units on this one. Find the tank's volume. Okay, here are a few keywords. Revolving. They also told us the axis they're revolving it around. That's important. Up until this point, it's been like all x-axis except for that one crazy one. It was the second one we did. It's that one right there. And we'll encounter more of those later. But basically, the important stuff is volume or revolving and x-axis. And they gave us the equation. And it's bound between that equation and the x-axis. So we're rotating it this way. So at any given point like here, the radius is given by that function. And so we do the same thing we've been doing. So it's just the same type of problem. It just has a more practical application for it. And this one is not going to be subtraction because there's not a top and a bottom. Now, if you're looking at that, you're like, well, there's the top and there's the bottom. Okay, whatever. Here's what we really have. We have the top, and we would rotate the whole thing around. So when you look at this, you're actually looking at a three-dimensional figure from the side. So this is kind of rotated around. And this is rotated around, and this is rotated around, and this is rotated. It's that kind of thing. All right? But they just gave you the top and bottom in this graph when it's really just the top that you need. And it goes from 0 to there. Where is there? Well, it's 2. I'm going to prove that in a minute, but it's 2. Okay, we can tell by the graph. But if we didn't have the graph, we could still figure it out relatively easily. All right, so we'll do that. We'll have that equation, all squared, 1/8 x squared, square root of 2 minus x, and that is squared, and then dx. All right, real quickly, I just want to verify that this is truly 0 and that's 2, more than just by looking at the graph. The 0 right here is where the function itself would equal 0. So I'm looking at this and I'm thinking, okay, what would make this equal 0? And we could do it in our head, but I think it's worth doing. Very early in AP Calc or, pre-calc, you probably had to find x-intercepts and y-intercepts when given craziness like this. So I'm looking for x-intercepts, and I know it's at 0 and 2, not just because of the graph, but because of this. And I would say, well, if it's an x-intercept, y equals 0, and I would take each factor and set it equal to 0. So here's that factor equal to 0, here's that factor equal to 0. And I'd get that, I'd solve it. So multiply by 8, take the square root. And either way, you're going to get 0, so x equals 0, boom. And then this one, you'd square both sides, and you'd have 2 minus something gives me 0, so x equals 2. And that's why those numbers are valid. Okay, this is one of those problems where I personally find it easier if you type it in under y equals. A little less room for error with parentheses, and did I square this, did I not square this, and where do the parentheses go? And I mean, relatively easy to figure out, but there's just enough room for error where I think it's best that we type it in. So there we go, we look at it, we make sure it's right, it is, and then don't think too hard. Math 9, 0 to 2 of y1 with respect to x. Whoa, I messed up. Man, I messed up. Okay, I messed up because I forgot to square it. Thanks for reminding me. Ah, cool, this one works out pretty neatly. 1/30th. So this is actually pi over 30. And if you wanted to, you could say pi over 30, and you get something close to 1/10, so 0.105-ish. There we go. Now, we're not done, because they actually gave us units. So this is cubic meters, and I probably should have put it here too, so cubic meters.